Hello, this is FlippedHarber for Physics. In this video we'll be talking about free fall. During the video we'll talk about a definition for free fall. We'll look at some examples of free fall and some examples of things that are not free fall. We'll talk about the acceleration of gravity and give a number for that. And then we'll talk about the symmetric nature of free fall. Now, free fall is any motion that occurs when the only force or acceleration acting on an object is gravity. So in true free fall, we even ignore air resistance. So really it's not possible to have free fall on Earth because the atmosphere around Earth impedes this downward acceleration. Now, the only true example of free fall that we can talk about is on the moon. But we'll ignore air resistance because we generally don't deal with objects that are going fast enough to really be bothered by air resistance. Another reason we ignore air resistance is it's really complicated. The actual equations for air resistance are huge, so we ignore it during our calculations. Now, examples of things that are actually in free fall: when a ball is dropped from a certain height, or if an object is thrown upward and then caught. Things that are not examples of free fall that you may be surprised by: anytime somebody is parachuting and that parachute opens, they're no longer in free fall because that air resistance is so huge that they actually stop accelerating. A plane is not in free fall. Okay? A glider, even something without an engine, is not in free fall because of the shape of the wings. There's a force called lift that is counteracting this downward acceleration from gravity. And really anything with an engine or a motor or any type of wing shape is not in true free fall. Even those little helicopter seeds that fall out of trees are not in free fall because their air resistance is big enough that they just don't fall properly. Alright, let's talk about this acceleration due to gravity. Okay? Now, this actual acceleration that we're talking about is caused by the Earth itself. Don't worry about why it's happening. Okay? That's a deep, dark secret of physics that you're not ready for. On Earth, we say that the acceleration due to gravity is 9.80 meters per second squared downward. Now, every single planet is going to have its own acceleration due to gravity. Okay, it's a product of a lot of different things. Again, we'll get into it later, but just suffice it to say, every single planet, every single moon has a different value that we would use. Okay, we use a lowercase g, obviously stands for gravity, when we want to talk about this quantity. Generally, we stick to the conventions that up is positive and down is negative. Now, that means that when you're working these problems, you're normally going to be plugging in a negative 9.80 meters per second squared for acceleration. Okay, can you flip it on its head and say that down is positive? Yes, but I actually suggest against it because you got to make sure you flip everything else. And I just would prefer you stick with the conventions. Now, this acceleration, every object on Earth is trying to accelerate down at this rate, even when they aren't moving. Okay? So if you throw an object up into the air, as soon as it leaves your hand, it's slowing down at 9.80 meters per second squared. At the very top of its motion, it stops just for an instant. It's still being pulled down at 9.80 meters per second squared. And then when it starts to fall down, it's still the same number. Okay? Don't try to use a different number based on where you're at in the motion. It's always the same number. Okay? Don't make it more complicated than it needs to be. Alright, let's talk about this symmetry of free fall. Okay? I want you to start by considering an object that's thrown straight up. So this orange ball that we see is thrown straight up into the air, has a nice high velocity as soon as it leaves the person's hand, but as soon as it leaves the person's hand, it's starting to slow down at 9.80 meters per second squared. And that means that it's covering less and less distance in this motion diagram on its way up. It's going slower and slower and slower. And we see that with these shorter and shorter and shorter velocity vectors. Eventually, at the top, just for an instant, it stops. Right at the very top, at the very tippy top, the velocity is 0. Okay, more about that in a minute. Now, if we let this ball now fall down, it's speeding up as it's going down, and it's speeding up at a constant 9.80 meters per second squared, and it's covering more and more distance on its way, excuse me, that's supposed to say on its way down. It's covering more and more distance, and we see that with the bigger and bigger and bigger velocity vectors. Now let's put the two halves of the motion together, and we can see that one side looks just like the other. Okay, the object is moving up or down at the same speed at any given height. So we see the two balls, which is actually the same object going up and then down at the same height, are going the exact same velocity, exact same speed. The only difference is that on the way down, that velocity is negative. Now, additionally, this is also important to understand. It takes the same amount of time for the object to go up and stop as it does for that object to come down to the same height. Now, if it gets caught higher or lower than it was thrown, that's no longer the case. It's going to be going faster or slower when it's caught. But if it's caught at the exact same height it was thrown up at, then it lands with the exact same speed. The only difference is that it's now negative. Okay, so here are some very, very important concepts that you need to get about free fall, really specifically about this up and down motion. The object stops just for an instant at the top of its motion. This is useful when we want to find the maximum height. We can set that velocity as our ending velocity, our v final, or we can actually turn it around and make that our v initial if we want to. Whatever is more convenient in our equations. Now, at any given height, the object is going the exact same speed. It's just going to be a negative velocity on the way down. And finally, when the object returns to its original height, it's going the exact same speed it was thrown with. Okay, so that's all we really need to talk about free fall. Most important thing is that the acceleration is a negative 9.80, and you always need to know that, even though they're not going to give it to you in every single problem. You need to know that that acceleration is a negative 9.80. All right, good luck. I'll see you in class, and I'll see you online.